Hi everyone, welcome to Mostly Math. Today we are going to evaluate these two integrals here, the definite ones, and we'll probably get to a few indefinite integrals as well. So to start off with, I'm going to use my favorite technique of complexifying the integral so we can evaluate one simpler complex value integral and get them both out. Let's, instead of considering both integrals separately, consider one integral. We're going to replace the cosine and the sines by a complex exponential. And we're going to simplify the argument of the exponential. Let's see, we want to have everything like this. We'll see why in a second. And I want it in this format because we know this integral just a standard result from elementary calculus, integral over all space e to the minus ax is simply 1 over the constant a. We simply have a complex valued constant here, but that's no problem for the time being. So the integral is done, but it's not useful now because we need to take real and imaginary parts to get these integrals here. Well, that's pretty straightforward. We'll just multiply by the conjugate of the denominator. That's just going to be a plus ib over a squared plus b squared, since of course any complex number z star is equal to absolute value of z squared. Or you can multiply it out. We see now that we have the real and imaginary parts in a form that we can write down the value of the z integrals here. It's just a over a squared plus b squared for the real term, the cosine integral. And the imaginary term is going to be b over a squared plus b squared. That's pretty cool. We got two integrals for the price of one. Favorite technique of mine, using complex numbers to make your life easier. It's possible to get these integrals by purely real means, though it's not as easy. I believe there's some Feynman techniques, I believe, that'll work on this. And this form is the one that you'll see in applications, like in physics. If you ever have an integral, it's usually not an indefinite integral, it is a definite integral, usually over all space as well. So that's why I wanted to start with this integral. It's easier to do than the one that we're going to do now. So it is possible to remove the limits of these integrals and still evaluate it. That's actually what we want to do next. We're going to make some modifications. We're going to remove the minus signs here to get rid of some pesky signs. You can, of course, introduce them later if you want. And let's get started on these integrals. We're going to do the same technique, basically. It's just going to be a bit more involved because you have less structure. You'll see. So let's go ahead and consider our new integral. That's e to the ax, e to the ibx, which we can of course write as the integral of e to the a plus ibx. Same as before, we're just going to evaluate this integral, and now we'll use the rule. If we have an integral of an exponential, just 1 over the constant times the original exponential. Totally easy to do. Constant just happens to be complex in this case, but that's okay. It's just going to be e to the a plus ibx over a plus ib. We're going to again multiply top and bottom by the conjugate. A minus ib here. So we can get the real and imaginary parts. We have a minus ib times our exponential. And we're going to have the modulus squared again on the bottom. And this is where it gets a bit more involved. We now have to expand the exponential into the sine and cosine form, which is not too hard. We have 1 over a squared plus b squared now. And we're going to have e to the ax just along for the ride. And we're going to have an e to the I bx, which of course we can reuse Euler's formula to simplify. Into cosine of bx plus I sine of bx. We see where the sines and cosines come from already, which is pretty cool. And I did forget the important a minus ib. Let's go back and fix that. Before all this, there's supposed to be an a minus ib. Bear with me, sorry about that. All right, and now we simply have to multiply the a minus ib times the cosine bx plus I sine bx, and we should be pretty much done. We do that now. Well, let's go ahead and write the real part first. We have a cos bx, and the other real part is going to be the last term. Minus I squared is equal to 1, of course. Yeah, it's going to be minus b sine bx. And now for the imaginary component, we're going to have a sine bx. Got that one. And we have a minus b cos bx. And now we can basically write down the values of our integrals. So our integrals now are as follows. We have integral with respect to x of e to the ax. Cosine bx is the imaginary part of the real part of what we had up there, which is simply e to the ax over a squared plus b squared times a cos bx minus b sine bx. And similarly, we have the integral of e to the ax sine bx simply the imaginary part of what we had up there, which has the same factor up front with a different trigonometric component. Let me just do a quick check to make sure I got the right solution. Let's do a double check, why don't we? Real part, a cos bx. The other one is going to be minus I squared is equal to 1. Yeah, I think I messed up that plus sign there. They shouldn't both be the same sign. Yeah, just one sign error. Hope you can forgive me about that. But this is the final result as I previously calculated it. And note, if you want to remember them, if you know one of them, you can take the cosine x and replace it with sine x. And you can take the positive sign in the middle and replace it with the negative sign. And that's how you can convert between these if we ever wanted to remember them. And I think it's pretty cool how you can use the same technique. Make sure I corrected it both places. Yeah, this one and this one. For sure. Now it's correct. I think it's pretty cool how you can use the same technique that we use to evaluate the simple or complex integral to evaluate the indefinite integral as well. I find it less useful than the complex valued version, but it's nice to know that it exists in closed form. And if you enjoyed this, want to see more math, please subscribe. See you next time.